Good afternoon. My name is Jerome Pearson from Star Technology Research. I'm a small business in South Carolina, and I'd like to talk about some of the transport options for the moon. And some of the material we developed in this talk was funded by the NASA Institute for Advanced Concepts. They funded us for a lunar space elevator study, and as a part of that, we did some additional work on other transportation options that would fit with the lunar space elevator. And my co-authors are Harry Wykes, Eugene Levin, and John Olson. If you look at the options we have for lunar transport, I think as far as the surface is concerned, we'd like to duplicate the kinds of things we have on the Earth. Roads for cars and trucks and buses. We'd like to have an aerial tramway for cable cars where you do not have to deal with the lunar surface and the dust and the grinding and all that. It'd be nice to keep away from the surface and stay above it, hanging on towers. And then, of course, there are flight options. There are ballistic rockets that you could use to transport material long distances, or you could even do lunar slings, which we have looked at in a little detail, and I'll talk about that a little bit later. On lunar highways, one can go all the way from an unimproved dirt road, which is basically what the Apollo lunar rover did, and that's what the Mars Spirit and Opportunity rovers did. If you saw the presentation last night with Steve Squires, he showed how they got stuck in the soil of Mars and all that. There's a danger in propulsion that way. So it'd be nice to improve the soil to have a better roadway. The first thing you can do is you just sort of bulldoze it, make it level, just avoid boulders, or push the boulders out of the way, and make a basic dirt road. You could even add a centerline conductor, which a robotic vehicle might follow to go from place to place on the moon. And then finally, you might want to pave the lunar soil to make actual highways and roadways and to cut down the dust. And in addition to work on lunar cement, which Professor Lin and Tang have been doing, there's been also work on trying to make pavement out of the lunar surface without any chemical reactions, but just by microwaving it. And Larry Taylor at the University of Tennessee, Knoxville, has done some work using microwaves, trying to center some simulated lunar soil. And he's had very good results. He just takes standard microwave oven equipment and applies the microwave energy to the soil, and it centers very well, produces a nice compact surface, and is a good way of getting rid of the dust. So what we might do is we could pave a wide road for standard four-wheel vehicles, or six-wheel vehicles, like the Apollo Lunar rover or the Sojourner Spirit. We could just pave two narrow troughs. If you have a four-wheel vehicle, you could have two wheels run in one trough and two in the other trough, sort of like a railroad track, to require less paving and less energy to do that. Or you could just do a single trough and have a vehicle like a motorcycle if you could balance it. Finally, you might create some kind of a monorail base with either concrete or centered blocks. If you look at what happened on Apollo, we have some examples of vehicles running over unimproved surface on the moon. And this graph compares what the Apollo lunar roving vehicle can do with what we expect other vehicles to do. This is the range in kilometers versus the storage efficiency in watt-hours per kilogram. The Apollo LRV used state-of-the-art batteries at the time. They're a little bit better nowadays, and they can get a range of about 45 kilometers. Now that was with a 700 kilogram vehicle and 456 kilogram payload. We might also have more efficient vehicles now, or more efficient engines and tires and transmissions than we did during the Apollo program. But if you just assume the Apollo performance and you put in current values for watt hours per kilogram storage efficiency, one could expect that with existing batteries, you could get about 100 kilometer range, and with fuel cells, you could get maybe 175 kilometers range. Now, I would expect these to be even better than that if you have improved vehicles and improved surfaces. The other problem that you have is how do you power a vehicle like this? What I'm thinking is taking material from the lunar pole, which might be ice or whatever, and getting it to a spot that can be sent to the Earth. Or you might go to a base that's out in the lunar area. So you might want to go a long way, like from the pole to the equator. That's a long way to go. And you might do that nicely during the daytime, but that's only 2 weeks out of the 4. And at nighttime, you've got a problem. How do you get your power? We don't have the range to cover the entire distance. So you either got to have batteries and fuel cells and gas stations or way stations along the way to recharge things as you go. One of the possibilities that we haven't really looked into is you could beam the power from towers or from orbit. There's been some work at the space elevator games in Las Cruces on trying to beam power to a climber that would be climbing a space elevator ribbon. And they have done some experiments where they beam the power from the ground. Right now they're just using solar power, but there is a possibility you could use lasers and so forth. And perhaps on the moon you might have a laser system that would beam power. But we're talking a long distance here, so that might be a problematic way of doing it. What you'd like to have is Highway 1 on the moon, basically from the lunar polar supposed ice deposits. You might go right up to the center of the near side, which is the location of, I think this is Surveyor 6, is that inverted yellow triangle there. This is Apollo 11, and that's Surveyor 5. So these are a couple of possible paths that you might go from the pole up to the equator. And with a battery range, you might be talking a couple hundred kilometers, and with fuel cells, perhaps 300. But what this means is the road is about 3,000 kilometers long, and so you can't make it at nighttime. During the daytime, you're fine. It takes you about 48 hours at a reasonable rate for these things. But and so at daytime, you can make it. You can make several trips during the 2-week lunar day. But at night, you're going to have to make 10 to 15 stops for gas. We don't have gas stations, but we could have solar power stations along the road that would be charging battery packs, and they charge it during the day, and then by the nighttime they're all fully charged. When your vehicle gets there, you just turn in your depleted battery pack, get a charged up battery pack, and just keep on going. So that's one possible way of getting the entire distance. Now, why would you want to go from the pole to the equator? Well, our thought is we're going to have a lunar space elevator, and that space elevator will come down at the equator. And what we'd like to do is we'd like to connect that with a transportation system that goes from there to the pole, so we can bring that lunar ice from the pole up to the equator, and then up the lunar elevator to Earth, to bring materials from the moon to the Earth, and also to bring supplies from the Earth down to the lunar polar station. So we've envisioned looking at a tramway, which would have a series of towers going from the equatorial connection down to the pole. Now it turns out the moon is fairly curved, but you could make about a 90 kilometer span with a 1 kilometer tall tower. 1 kilometer seems kind of tall for a tower, but on the moon with 160, perhaps that's not too bad. Also, if you go through craters, you can go a pretty long distance if you go from one rim of the crater to the other and still have a lot of sag in your tower. We've looked at several kinds of Earth systems for towers and tramways and so forth, and the model for this is the ski ski lift. And there are a lot of those examples around the world that we can look at. And you have small, sometimes enclosed vehicles that can cover inclement conditions, and that would fit well for having an enclosed capsule on the moon. There are construction techniques for towers, which are very lightweight, compact, and very easy to assemble. This is one called a tensegrity tower. It's about a third of a pound per foot on the moon. So very lightweight. Would not take much to construct these, and can be built for very tall heights. Here's an example of the span that you can get versus the tower height, depending on the sag you're willing to accept. This is the span in degrees, and 1 degree is about 30 kilometers in latitude. And this is the sag that you're willing to accept. If you don't take any sag, you can't get any span. But if you take 80% sag, you can get way down to here, and here's a lesser number. So if you look at something like we started looking at 1 kilometer tall towers. That's this curve right here. You got a pretty good span there with 40% sag, and that's pretty good. But if that's too difficult to build, you can even go something that's just 100 meters high, and even 100 meters high, you can get basically a 1 degree span. That's 30 kilometers. That's not too bad. So we envision a lunar space elevator that connects with a lunar tramway, which you might call the Polar Express, because we're going from the equator to the poles. And what you would do is you would have this thing run from one interesting point to another between the equator and the pole. You might have possible mineral deposits at various spots. Places where certain minerals are more plentiful. Down at the pole, you would have water ice mining and perhaps use that for propellants. And then perhaps you might have more of an installation at the equator where you could have possibly habitats, factories, regolith mining, and so forth. And the lunar tramway would carry supplies, equipment, materials back and forth between these and all the way to Earth orbit. At the top there, we've done a sketch of what one of these climbing vehicles might look like. This vehicle can be used as the tramway car, and it also can go up the lunar space elevator to be dropped off to head for Earth orbit. Once it's climbed the tower under solar power, these are the solar panels on the sides of the thing here, which you don't seem to find this pointer here. Okay, these are the large solar panels. So a lot of the vehicle area is the solar panels, and then this is the ribbon that we're attaching to, and these are wheels that go along the ribbon. You could actually have this thing go drop off the lunar space elevator and use an ion rocket to go from there to high Earth orbit and bring things from the moon to Earth orbit, and then take things back to the moon. Once you do a tramway, this allows you to do other kinds of things on the moon. Here's an example of how we might mine a polar crater, which is in constant darkness, for water. You would have a series of cables that go from the rim across with a sag, and you could have a vehicle that could move along these things, and by moving the vehicle, you could have access to a large area of the base of the crater, and then you'd have a place a little bit nearby where you can get power, clip a certain amount of power to do collection. We've done some figures on how much your material would be getting, collection temperature and so forth, and then the power to be required, which is 110 kilowatts. If this is being done near the lunar pole, you can find perhaps a spot that is in basically constant sunlight and get your power almost constantly while the crater is in the shadow. You might even have a kind of a ski lift device that could take you along this tramway. I'm not sure it'd be too comfortable, and you're talking about a 2-day trip from the pole to the equator, but you could do it with perhaps a few stops and all that. I've been crammed in something about this tight, I think, on flight from Chicago to Hong Kong. It was 18 hours long, so if I can take 18 hours on that, maybe these guys can take 24 on something like this. Now that's ground options and tramway options, but there are some lunar flight options. You can do ballistic rockets. You may recall that Airbus they had in 2001. That's a very inefficient way of going. It sort of floated above the lunar surface for a long time with constant thrust and so forth. You can use an ideal mass driver, and you can use what we would propose as a lunar rotating tether sling. If you throw materials, say from the pole to the equator, then you have the problem of landing when you get to the other end. And you could either land by having a rocket stage on there to slow it down and have a rocket, or it has been suggested that you could actually crash it into the lunar regolith and let the friction slow it down and stop it. And if it's just pure cargo and containing materials, that might survive. We like the idea of the lunar sling, and here's an example of how this might work. You'd have an installation on a hill, and we're assuming something like a total altitude of about 4 kilometers from the base. And you put the thing on the top of the hill, and you have a long tether that's out here, two-ended, and you put materials on the ends of the tether, and then you extend the tether as you rotate it with the power supply, and you run the tether in a circular, and you increase the velocity of the tip until finally, if you want to go to low lunar orbit, you have about a 12 kilometer radius, and you can get a velocity of about 1.68 kilometers a second. The tip takes about 24 Gs and 100 kilowatts, but you can do 3 tons a day that way. Going a little faster, if you get up to 2.38 kilometers a second, you can go to escape or to L1. And some people have proposed that L1 be the place that we use as a gateway for travel to and from the moon. So if you get material at L1, then you can take it from there to the Earth by some kind of vehicle. So this would be fairly productive several times per day on 100 kilowatts. And the way you would do this is you would be throwing things with ballistic trajectories from your launch point. If you had a bare payload, you could use a crash landing. If you want a soft landing, you could use a rocket stage. Now the plumes give you a little pollution and so forth, but the sling does have the advantage that it can sling payloads anywhere and doesn't use any fixed surface paths. In that sense, it's a little bit more versatile than the O'Neill mass driver, which is typically fixed azimuth, whereas the sling, just when you release it, determines where it's going to go. And you can also cut down the vibration and the dynamics by releasing 2 payloads in opposite directions at the same time. And if you time it right, you can actually have both payloads go to L1 or both payloads go to the equator. So in summary, the transportation options we looked at were, we think the most promising one is the microwave paving to make highways that you can follow. And we think there's a way to solve the power problem at night by just having storage or charging stations along the way for long-range vehicles. And we'd like to integrate the lunar tramway with a lunar space elevator and make a unified transportation system. But at the same time, we could use lunar slings independently of that to throw material from the pole to the equator or even to L1. And that's the end of the talk. Thank you very much. If we can get the lights, I can answer any questions if you have any.
Yeah. What about electric rail?
There was a question, what about electric rail?
You said, what about an electric rail? You're talking about electrifying a line there and then running the vehicle off the power from the rail. Yes, you could do that if you could transmit the power over that long a distance. You're talking about a 3,000 kilometer transmission line, basically. You have to worry about losses and so forth. But yeah, that's not impossible. You could have a long conductor. We were looking at trying to use as much lunar materials as we could. You take a device and you microwave the regolith. It doesn't take a lot of earth materials. And our goal was to just use the ribbon from the Earth as a high-strength composite. Everything else is done locally. Okay, I'm sorry, you had a question back here? The Lunar Space Elevator, you probably missed my earlier talk. I talked about Lunar Space Elevators earlier. Lunar Space Elevator is like the Earth Space Elevator in that it's balanced about a synchronous point. In the case of the Moon, that's the L1 and L2 Lagrangian points. And that's about 62,000 kilometers toward the Earth on L1. And it's balanced about that point, and it extends above that point because you have a counterweight. The counterweight has to counteract the weight of the cable below the L1 point. But the whole thing's about in balance about that, and then once you've done that, and you have a counterweight, then you can lift loads up that Lunar Space Elevator into space. And once they go past L1, you have to put power in them to get them up to L1, but after that, they'll fall free past L1. You can just let them slide on out the Lunar Space Elevator cable and let go where you want to let go. And depending on where you let go, you end up in high Earth orbit. And you can choose an orbit that goes down to, say, GEO or even lower if you want to. It's an elliptical orbit, and then you can use ion rockets to circularize and get into Earth orbit. And then to come back, you can take the same vehicle, use an ion rocket to go from Earth orbit to lift it to get to rendezvous with the Lunar Space Elevator, attach to the top of the Lunar Space Elevator, climb down past L1, and then slide down to the ground. So it's a complete integrated transportation system from Earth orbit through the Lunar Space Elevator down to the lunar poles using the tramway. Any other questions?